Okay, can everybody hear me? Will nobody hear me? Anyone? 50-50? Okay. So good morning, everybody. Time for our last lecture of the week. Couple things. Reminder about the cell phones. Did the watch alarm go off yesterday? Or did we? No. Oh, excellent. We had. We would prefer not to have the watch alarm. That would be my preference. Actually, I never heard it, so for me it wasn't a big problem. So we have some films today. There's A World Without Antibiotics. That's at 11:15. There's A Beautiful Mind at 1:15. And Persuasion at 3:30. Sounds like they're giving you easier ones today. These both, I know those last two. I've seen them both. Did anyone go see the Higgs Boson yesterday? How was it? Oh, Fabiola Gianotti. Yeah. Oh, okay. Was it good? I haven't seen that one. Medium good. It's okay. It doesn't have to be good. She's usually a fun speaker, actually. Right now she's in Davos at this World Economic Forum. She's actually the co-chair of it this year, which is pretty cool. Yeah. Okay, well, let's get started. So today's going to be actually two things. It's kind of going to tell you a bit, we've talked a bit about, what is the Higgs, how do we see it? Now we're actually going to go back and say, what have we measured about the Higgs and learned? So what do we know about the Higgs so far? And then give you some ideas about kind of what we don't know and why we might be interested in it. So it's kind of a bit more wide-ranging today. So first of all, here's the final slide. Now it has all the links, including today's lecture. If anyone doesn't get a chance to get it down, come by afterwards to do it, because obviously once this is gone, you can't get it. Just a tip, if you get the last one, of course you can get all the individual ones. They're inside it. So if you just get one, go for the one at the bottom. Oh, you can't see it. It's YD787QSU. I'll say it again. YD787QSU. You'll also be glad to know I brought my own ones today. So hopefully there'll be a bit less coughing. It's the downside of having very small nephews and nieces. They tend to pick up all sorts of things. She's more unhappy than me, though. Exactly, of the wrong sort. Okay. Oh, sorry. If everyone wasn't finished, one more second. Okay, then let's get going. So here again, remind about the reading material. And now let's get going. A bit to remind about what we did last time. So last time, we talked a whole bunch about the detectors that we use to track particles. So these were the tracking detectors. We talked about the two types, the silicon ones, which tend to be really on the inside, and then we talked about these muon detectors, which are on the outside. The reason we were talking about that is saying how we actually can reconstruct muons and electrons, because we needed that to see the Higgs to ZZ. Then we talked about the other way we saw the Higgs when we discovered it, which was via the decay of the Higgs to Z bosons, and then to either electrons or muons. And these are the two plots from that time. This is the one from Atlas, which is the one we saw in the animation. And here, that's the Higgs that you're spotting. And this is the same one from CMS. And again, the Higgs is this little guy there. Sorry, I went for the wrong one. That's actually a Z boson, by the way, this other peak that sits over there. And this was a really exciting time. This is the seminar at CERN, where the discovery of the Higgs was announced, which resulted again in the Nobel Prize in physics for Peter Higgs and Francois Englert. So that's actually a while ago now, right? This was 2012. We're now in 2018. So that actually means it's 6 years ago. And it doesn't mean that I've been lying on the beach for the past 6 years. Actually, quite the opposite. We've been pretty busy. So I mentioned that we've already made 5 million Higgses at the LHC. Unfortunately, we haven't been able to keep all those Higgses. In fact, most of them we had to throw them away immediately. But nonetheless, this is a significant chunk, and there's actually quite a bit that you can do with this if you want to start learning. Now, has anyone heard of the PDG, or the Particle Data Book? Nobody? Oh, that's a bit sad. So the Particle Data Book is essentially the encyclopedia of physics. And so it gets published every year or every 2 years by a group, which are the Particle Data Group, oddly enough. And they're actually back in Berkeley, where I work in the United States. Now, the cool thing is if you go here, this is their website. you can get all the information. It has a whole bunch of articles all about particles. You can actually also get your own copy. So they'll send it to you anywhere in the world. And it's this little book like this, and it has all the different particles listed in it, all their properties and everything like that. So this is pretty nice. They also make that particle adventure site, the one that I think I suggested you have a look at. Now, the reason I'm showing it here is this was the next step. We have this encyclopedia of all the different particles. We need to put the Higgs in the encyclopedia, and we need to fill in all the different pieces about what we know about it. And so this is a zoom showing you a little bit what the entry is. And this is the sort of typical things you want to know about a particle. You want to know its mass. You want to know its spin. We'll talk about spin. We haven't really talked about that yet. We want to know something called the decay width. That might sound weird. That's actually just a measure of the lifetime. You know, we've talked about how the Higgs is just around a short amount of time. It's actually the inverse, but you can do 1 over to get between the two. Then you want to know about all the different decay modes. This we've talked about a bit. We've looked at 2 of them. We've looked at the decay to photons, and we've looked at the decay to Z's. But to get a full picture, you really want to measure all the different ones that you can get. Okay, so actually we're going to start with the spin, which might not necessarily be the easiest one. I think I'm going to need water too. All right, so here's a nice little picture. And I need you to do some imagining for this part. So first of all, spin is a property of a particle, okay? It's not actually spinning. So the idea of an electron sitting there spinning around, this isn't true. It's simply a property. But the reason we call it spin is because it kind of works a bit like if it was spinning, okay? What we mean by that is when we write down the equations, it behaves similarly to the equations we would write down for something that spins, but it's not actually spinning. And if you imagine you have it spinning, you can think about it. It can spin in 2 ways. You look down at the top of it. It could either be spinning like this, it could be spinning clockwise, or it could be spinning counterclockwise. But they're just 2 choices that you have, right? If you want it to be just going transverse to wherever you're looking from. Does that make sense? That's important. And so actually we give it 2 names. We call it left-handed or right-handed. And that's simply, it's the same idea. You can think about it as people being left-handed or right-handed. Electrons and protons, they can all be left-handed or they can be right-handed. That's maybe the nicest way to think about it. And then I mentioned this a few times. This is the difference between the bosons and the fermions. The bosons, they all have integer spin, and the fermions, they all have half integer spin. And so the bosons, it's usually spin 1. The fermions, it's usually spin half. And these are the just properties of them. And then that tells you a whole bunch of different things about them once you know that. Now, there's another thing which is called parity. Who's heard of parity? Few people. Parity, the best way to think about it, is if I do some physics reaction, you know, like I make my Higgs and I decay it to Z bosons, and I look at it in the mirror, does it happen in exactly the same way or not? So if parity is conserved, what it actually means is if you took the mirror image of it, you would actually see exactly the same reaction. And this is something one could either be true or not. And the actual way it works is it depends on which of the forces you're thinking about. The strong force, this actually conserves parity, so you could look at it in the mirror, it'd be the same. The weak force, on the other hand, absolutely violates parity. So if you look in the mirror, actually you don't even get the reaction at all. And so this is it. But the way you can think about parity is whether if you look in the mirror, does it still look left-handed or does it end up looking right-handed? This is how you could actually violate parity or you could conserve it. And so these are some of the properties of particles. They can all have these spin and they can all have these parity. And these are just things that we want to know because they actually tell us a lot about how the particle actually behaves. Any questions on this? Did anyone understand it? Too quiet. I think that means no. Yes?
This is what you explained it simply is just a lot of maths, really.
Of course. It's all equations. But this one is not a bad way to think about it, because if you actually look at the equations, they do what I'm saying. You know, sometimes I'm giving you metaphors, perhaps for the Higgs, for example, these are really metaphors. This one I'm telling you how the equations work. So this one is actually a bit more close to the truth than some of the others. So that's one thing. Sure.
Normally, if you look at yourself in the mirror, you have a mirror image of it. which is not identical to
Yes.
Now, if you would be totally equal, what's the word? Equal?
Symmetric.
Symmetric, yes. Then you would have the same mirror image, am I correct?
So the question was, she was saying when she looks at herself in the mirror, she sees a mirror image of herself, right? Which is not the same. Most of us are not symmetric, right? The left and the right is a bit different. And was asking if parity is conserved, would that mean that you'd look identical? And the answer is yes, if you want to think about it. But here we're talking really about particle decays, how they look in the mirror, not the particles themselves, if that makes sense. Okay. Now the Higgs actually is special because it turns out there's actually only one spin zero elementary particle, and this is the Higgs. So I just explained what spin is, right, and talked about spin half and integer spin. What we actually think is that the Higgs has no spin at all. It's spin zero. And this is kind of weird, and what it means is that it obeys a whole bunch of different equations that no other particle does. So that's kind of interesting, and also kind of weird. There's another one. It's also predicted to have positive parity. So particles can either have positive or negative parity. And the prediction is it positive? So you can imagine we found a particle. You know, I showed you this peak. All that tells you is there's a particle, decays to photons, and it decays to Z bosons. Doesn't tell us anything else, right? It could be any type of particle. We don't know. And so this was the first thing we wanted to figure out is, are the spin and the parity of the Higgs exactly the same as what is predicted? Now, the way you do it, I don't want you to understand this picture. It's way too complicated. What it's actually showing you, by the way, is what happens when you have a Higgs decaying to two Z's who decay to other particles. That's not the point. The point is, you can imagine, think about this in 3D space. You're going to have these two electrons and two muons, and there are going to be various angles between them. Right? You imagine if he goes out there, you could think about looking at the angle between them. You could look at the angle between where they were produced. And it turns out that if you measure those angles, it actually tells you about the parity and the spin of the Higgs. So that's the idea about it. It's trying to look at which way do all the particles that get produced move. So here's one example. I've been showing you a few plots, so hopefully they're starting to be a bit more familiar. Doesn't matter what's on the x-axis. Some magic variable, actually about a year of work of someone's life. We're not going to go into it. But what we are going to look at is these black points. These are the data. So this is, what came from the LHC? What did we figure out for this distribution? And the question you want to ask is, do you think the black data looks more like the blue histogram, which you can see here, or more like the green dotted histogram? Votes. Who would like to vote for green dotted? I got 2. Who would like to vote for blue? Oh, good. Majority wins. We'll go with democracy. That's correct. Now, of course, the real way we do it, right, is that's how we do physics. We all sit there and vote. No, actually, we have statistical tests, right, which actually take the data and the uncertainties, because those are important, and ask that question more quantitatively. But what it actually is, by the way, is the blue one is the standard model. So it's zero spin, and this is doing weird things, and positive parity. The green dotted one would actually be if it had spin 2 and positive parity. So this would have been a different type of particle. If we found that, we would have said, oh, wow, standard model is completely wrong. And that's how you do it. You just want to compare between the two. And this actually tells us, this is how we know, that this actually is the Higgs boson. At least it has the spin and the parity as predicted. Yeah.
So the Higgs has no negative parity.
Yes. So parity, the way it works is it can either be positive. Sorry. Yeah.
There's a balance then outside. Positive nucleus and the negative electron. There's a balance. And you're saying there's no balance with the Higgs.
Okay. So the question was about how parity might relate to charge, which you have inside atoms. The truth is, when I say positive and negative here, I'm not talking about charge at all. I'm just talking about, imagine there's a thing like, counting up apples. It's really something completely different, right? You can have 5 apples, you can have 10 apples. Parity is another thing, and it has absolutely nothing to do with charge. And so you could think about the positive and negative, as I have an apple which I took from you, or you have an apple which you took from me, which would be negative. So it's nothing to do with charge or anything like that. It's just another property. Particles have lots of different properties, which we really try to actually to measure.
So sorry, in the previous slide,
Yeah, we can go back.
blue and the green were the results of the mathematical simulation of what you would get, assuming spins off whatever.
Yes, so the question was, how do we get the blue and the green curve? This is a good question. It's a lot of work, actually. The answer is that we have the theorists who would make a prediction for what would happen in those two cases. They make a prediction, and actually we do another step. We simulate the whole detector to see what we would actually get out. And then we compare that to the data that we have. And so that's how we do it. It's actually a lot of work, by the way, getting that prediction to compare to the data. Yes?
Sorry, me?
Yeah?
Yeah. I'm struggling because why are we going back to the standard model to predict Higgs?
So this is always so the question was, why do we go back to the standard model to talk about the Higgs? Because the Higgs is actually part of the standard model. So it was the last particle in the standard model. So it's actually part of it, if you want to look at the complete standard model. It would be other particles that would be outside the standard model.
And are we now beyond the standard
Not yet.
model?
We're getting there. Have to get another 10 slides or so, and then we'll talk a bit beyond it. Higgs is still firmly in the standard model. But actually, if this test had failed, if on the other hand we'd found that it had 2+, then we'd be outside the standard model. So as long as it behaves the way we predicted, we are indeed in the standard model. I think we can skip this one. It's the same thing, just visualized in a different way. All right. So we're happy with the spin. We're happy with the parity. Next one, let's look at all these different decay modes. So I've shown you this plot a few times, right, because it's the only one we have. This is how, in the standard model, we predict the Higgs would decay and how often it would decay to all these types of particles. And we looked at these very rare ones, right? We've looked at 2 photons, and we've looked at 2 bosons. So actually what's been a huge amount of the work over the last 6 years is actually to try and measure as many of these as possible, right? We want to check all of them, because you could check, does each number agree? Like if we looked at the Higgs decaying to bottom, anti-bottom, is it actually 57? Does it decay to this at all? We can also add them all up. And we can check, does it add up to 1? Because it needs to actually add up to 1. And so there are a lot of different tests that we can actually do. And that's what I work on. I actually worked on this one, and I've also worked on this one as well, looking for bottom and looking for decays to charm. And you can actually make this very pretty plot, which I want to explain to you because it's actually kind of nice. So remember I've said a few times that the Higgs makes mass. In fact, I've probably said that at least 20 or 30 times. Now, it's actually more than that. We need to say that the Higgs decays more to heavier particles and less to lighter particles, because this is what would come out. So what this is showing you is, let's take a whole bunch of different particles. We've talked about all of them. This is a muon, this is a tau, bottom quark, WZ, and a top quark. And what we do is we line them up according to their mass. Okay? So we put the muon way at the bottom here because he's very light. Put the top quark way at the top because, well, not at the top, at the right, because it's very heavy. Right? So we look at that. Then what we do is we go make our measurements, we look for the Higgs decaying to them, and we ask how often does that happen. And that's what we plot on the other axis. So we say it actually doesn't decay very often to muons, right? It decays very, very rarely. Where on the other hand, if you look at the W and the Z's, this is something that happens a lot. And what we notice, and that's what you see with this line, is that it actually all works the same way, that it's actually proportional. So what that straight line means is that the way the Higgs decays to each particle is actually proportional to the mass of the particle. So what I was saying, the heavier a particle, the more often the Higgs will actually decay to it. And so this is pretty powerful to be able to see. That's giving us another piece in the puzzle saying this is really the Higgs boson. It's really the thing that's actually giving the particles mass as we would expect. Any questions on this one? It's a complicated plot.
Must have given you some satisfaction when you saw this.
Of course. Each of these chunks that I'm showing you, and the question was, does it give us satisfaction? The answer is definitely yes. because you have all these predictions. It's like a puzzle, right? We have this whole long list of all these things that should be, and you get to check them off and do them. The funny part is, like, each of these black dots, that's about like 2 or 3 years' work of about 70 people. You get to make one black dot. So in that sense, it's a very, very condensed way to look at things. It's very nice. Yes?
Can you just explain the vertical axis?
I didn't fully explain the vertical axis, but I'm explaining partially. What it is essentially saying, like, actually, let's go back to this plot. All right. So in this plot, it shows you all the different particles the Higgs might decay to, right? It also says how often it decays, right? So you can see all these different numbers. Now, the y-axis is effectively, it's not exactly numerically the same, but it's effectively a measure of how often the Higgs decays to each of the particles. And so it's checking this prediction. It's saying, here's this prediction, let's check, and let's see how it works. There's a little bit of a transformation. That's why it doesn't go in quite the same order that you see. It's actually the coupling, to be precise. So there's the decay rate, which relates to the coupling. So yeah, this was a very, very nice one. And again, giving us another chunk of evidence to see what we have. So now we're going to spend a while talking about the mass of the Higgs. Now, we've all been saying, the Standard Model predicts a lot about the Higgs, right? We've shown how it predicts the spin, predicts the parity, predicts what it decays to. Actually, what it doesn't predict at all is the mass. This is actually what's known as a free parameter in the Standard Model, which means it actually could have had any value at all. Now imagine back 20 years ago when you're designing your experiment, that's pretty difficult, right? Because I told you that how much energy you have tells you how heavy a particle you can see, and you're looking for a particle and you don't know what its mass is. That's pretty tricky because if you guess wrong, what's going to happen? You're not going to find anything at all. So it actually turns out that 2 other accelerators already tried to find the Higgs boson, but they didn't have actually quite enough energy. And so this was the LEP, which was the old accelerator at CERN, and also the Tevatron, which was an accelerator in America. The LEP was very close. They actually got to 120 GeV. Turns out the Higgs mass is 125 GeV, but if you don't have quite enough, you can't actually get there. So this is something interesting. So it just is a free parameter. Of course, this means we want to measure it. Now, I told you it's heavy, but maybe one way to sort of get a feeling for how heavy it is to compare it to a gold atom. So in the units that we're working in, these are particle physics units, a gold atom would actually be 200 GeV, and the Higgs is 125. So you imagine it's about as heavy as a gold atom, but that's actually pretty impressive. Remember what's inside a gold atom. Remember, it has all those protons, all those neutrons sitting inside. We're talking about one particle, one point-like particle, which is as heavy as that atom. So it's actually much more dense if you want to think about it. I mean, density is the wrong concept because it's point-like. It has no actual size, but it's a really heavy thing. So if we had a Higgs boson coming by, this is something, that would be really quite dramatic to be able to see. Say again? No, so the question was, do we collide hydrogen atoms? The answer is no, we collide protons. We actually strip off the electrons and just collide the 2 protons together because we couldn't actually accelerate a hydrogen atom. Remember I talked about how we need charged particles to be able to accelerate them with the magnets in the collider. This is exactly right. So this is what I was talking about, how mass and energy can be viewed as the same thing. So I was asking, how do you get from one hydrogen atom to all those things? The point is that we collide them together, we destroy them completely. We don't care that they were protons, it doesn't matter. We take that energy, and then we can make different massive particles. This is that formula, E equals mc squared. And this is how it works. You could, but the point is, so the question was, can we make gold? Yes, we could. The problem is gold is actually would take some time to form. Because in order to get gold, you need to make all those individual protons and neutrons. You need to get them all close together, all at the same time. So it's very unlikely that it could happen, but it's possible. Basically, everything's possible. Yes?
Inside the cell, you have got some structure. Do they do anything in the cell? I don't know what you do. You get that speed, you can then analyze it. But when it's in the cell, does it do anything?
Okay, so the question here was, if we think about cells, and imagine that you have a Higgs boson inside the cell, what would it do? The answer is not much on the cellular level, but it would do the sense of making those protons and neutrons. So you need the Higgs boson to make the masses of the protons and neutrons inside the atoms, which make up the cell, but there is no interaction on a cellular level to think about with the Higgs boson.
Once it's done it, that's when it doesn't do more, does it?
So this is complicated. So you're asking, is it like the Higgs comes along, gives mass, and runs away? This is the question. So this is a picture. It's not quite right, because the Higgs is doing it all the time, in some sense. It's not like it just gives mass and then it's gone. The mass actually comes from the interactions of the particles with the Higgs field, which is there all the time, right? And it's essentially, you could think about it, it's happening on and on and on. And it's not that there's an actual Higgs boson that comes along and does it, it's more the interaction of the field. So here I jump back into the picture of the field. It's difficult because the Higgs is both this field and a particle. And sometimes I talk about one and sometimes I talk about the other. I agree, it's difficult. All right, let's go back to the mass. So let's measure it. These are the same plots that I've shown you before, right? The one on the left, this is the one from the photons that we had a look at on Wednesday. And this is the one from the Z bosons. And actually, it's pretty easy to measure the mass. What you need to do is you need to make this picture. You need to go and say, where is that point, right? This one where it's actually the highest, that's actually how you measure the mass of the two of them. So I think we could just take these plots, we could all take our rulers, and we'd have a measurement of the mass. Of course, we actually want to do it really accurately as we can. So now I've got 2 slides of equations. For anyone who doesn't like equations, please go to sleep for the next 2 slides. For anyone who does like equations, have a look. Because I actually wanted to tell you just for a second how we actually measure mass. Okay? And so we need to see some formulas. So the first one, maybe here I want, where's my little guy? Here. Okay. So there is a formula which comes from this E equals mc squared, right? Which tells us a relationship between mass and energy. Actually, that's not the full formula. You also need to add in the momentum, okay? And what it turns out is there's a relationship between the energy and the momentum and the mass. And this is always true. This is one of these conserved things that's true no matter where we go. Now here, this doesn't really matter. This is just taking the momentum and breaking it down into its components. We're in 3-dimensional space, so it actually has 3 components in different directions. So it's just expanding this p squared into its components. These are actually, for those who've seen relativity before, this is actually, we're using something called 4-vector notation. Who remembers vectors? Yes, lots of people. Excellent. So we just take a vector and we add one more. Easy enough. Well, they behave a little bit differently, but it's the same idea. And all it's doing is it's taking out the components of the energy and all the different momenta. Okay, so that's the notation we're using. Now, think about our Higgs boson. And in each case, we've been talking about it decaying into 2 particles, either 2 photons or 2 Z bosons. So what we do then is we take the energy and the momentum of that Higgs, and we say it decays into 1 photon and another photon. And actually, because it sums up very simply, it's really just a plus between the 2 of them. So if you want to know what is the energy of the 2, take 1 photon plus the other, you get the total energy. So this is how it works. And here it's just taking it, putting it into 1 together. All okay? Any questions on that for those who want to do the math? No questions. So this is the same thing. So we were talking specifically here about the Higgs decaying to photons, and you reconstruct them in the calorimeter. Right? We talked a bunch about that. In the calorimeter, it tells us the energy of the photons. But it tells us one other thing. It actually tells us where we saw the photon. And if we use that, we can actually figure out what direction the photon went. So now we can actually do some mathematics with this. It's the same equation I was showing you before. you can actually make some angle between where the photons go, and actually what you end up finding is that you can calculate the mass from the product of the photon energy or momentum and the angle between the two of them. So that's actually how we do it. All we do is we look where are the photons, we figure out what is the energy of photon 1, energy of photon 2, and what angle do we actually have between it, and that's actually how we got that Higgs mass that I showed you. So what I mean is, if you go back to this plot here, that's actually how we make all the entries in the plot. We do that for every single event. Any questions on that? It's okay, time to wake up again for those who went to sleep. All right, so now I'm showing you another plot, but this one's pretty easy. All we're doing is we're writing down the mass of the Higgs boson. And I've told you it's already 125 GeV. And all these pretty dots, these are different measurements. So it's like, take the ruler, figure out, what is the mass, done by ATLAS, done by CMS, using photons, using Z bosons, and you can see all the different values that you get. But all I want you to look at is this guy, which is the final one, which says that the mass of the Higgs boson is 125 GeV. Actually, that's the easy part. The hard part of this, figuring out how well we know the mass of it. It's easy enough to say the mass of something. Do we know the mass with 100% uncertainty? Do we know it very, very accurately? This is where all the work comes in. And actually what the uncertainty is 0.024. Okay? So what you want to do is you want to compare this number to this one, and what you can actually see is that we're dead certain about the 100. We're dead certain about the 20 and the 5, but once we get here past the decimal point, that's where the uncertainty comes in. And what that actually means, if you divide the two of them, we're actually at 0.1% accuracy already on the Higgs mass. So that's pretty impressive if you think about it, and that's actually where all the work comes in, is to get it down to this extreme accuracy. And by work I mean is calibrating the detectors, understanding photons, understanding electrons and muons, to really get that to be this precise. And this is what we actually have already.
Is this an example of the...
Seems to be outside. Sorry, 1 second.
Is this an example of the...
Sorry, just hold on. Let's figure out what's going on here. Oh, it's gone. Okay, go ahead.
where those who do the experiments approve the maths, as opposed to the maths coming first and then the experiments come back?
Right, good question. So she was asking, is this where experiments have confirmed the maths? Maths, we actually say theory. This is normally how we call it. Or if it's been a theory and then confirmed by experiment. This is one where the theory had no idea at all. So this one is actually where the experiments did a measurement and told the theory what it is, and then they learned a whole bunch of other things. So it's probably the most important thing we've learned about the Higgs so far, because it actually tells us all sorts of things about our theories. This is the thing that's really changed things the most. After saying there was a Higgs, the next one is what this mass has actually told us. So I mentioned it's this free parameter, which has absolutely no theoretical prediction. And you might wonder, should I care about this? This sounds awfully complicated. You have to do all this math. You have to make all these detectors. Should I care? Well, maybe you should care. So who cares about the fate of the universe? Oh, okay, one person. Okay, good. Everyone else doesn't mind. Doesn't really matter. All right. So it doesn't really matter. Well, you might care. All right. So what this is this is another plot. I'm showing you lots of plots today. But guess what's on the x-axis again? Mass of the Higgs boson. And actually what I put on the y-axis here is the mass of the top quark. Okay? Another one of those particles. Turns out if you do that, you get one dot. That's where our experiment actually gives us the value. And then you can see these colors. This is the theory. Okay? And you might be noticing what it's saying, and you might be guessing what that means, because the green one is actually saying that the universe is stable. Okay? That sounds good. The yellow one is saying it's metastable. The red one is saying that it's unstable, or instability. And what you notice is that we're actually sitting here on this edge of metastability. And so what that's actually saying is, if this is true, okay, and we have to have the theory be true and the experiment be true, and it's early days, so these things can change, it's saying that maybe our universe isn't perfectly stable. Maybe we're actually really on the edge here between having a stable universe which would last forever, or a universe that might actually decay according to some of these quantum fluctuations. So yeah, you might want to care about the Higgs mass to know if this is the case. Yes.
Using the same language as I am, meta means beyond.
No. So in this case, I'm using it the other way around. I'm saying it's partially stable. Yeah. And it's kind of weird, by the way. So it's kind of interesting that we're right on the boundary. Maybe that's telling us something that we don't know about our theory. Yeah, exactly. But don't worry, by the way, we're talking long time scale, so it's not like tomorrow. So I don't want everyone to go home and say I told them the universe is ending tomorrow. We're talking really millions of years. Yes?
The film, Particle Fever, he was talking about chaos versus the standard model.
Mm-hmm.
Is that what he was talking about? In other words, instability would be chaos, as referred to in that film.
A little bit.
Stability would be the standard model, as they know it, as they want to build on.
So the question was, in particle fever, they talk about chaos and they talk about the standard model, and is this the same as what I'm talking about? Not quite, because there are other theories that they could be around that aren't quite the standard model. But here, when we're saying unstable, we really mean that some of these quantum fluctuations, and these quantum fluctuations are making all the particles, might actually mean that the universe would eventually decay. So it's a little bit different. It wouldn't be chaotic, it would just be gone.
So I realise it's important to know where we are. There's not much we can do about it, is there?
Well, who knows? She was saying it's important to know where we are. Is there anything we can do? I don't know. Maybe we can figure out. I mean, you could ask the same question, does it matter if we know an asteroid is heading for the Earth? I think it's kind of useful to know that, because maybe we could figure out a way to stop that asteroid hitting the Earth. I don't know yet. This is very early, very speculative. More questions?
You want to go back to the previous slide?
This one?
The one before that, sorry.
That one.
Kind of was. Just on a lighter note, Lord Kelvin was quoted in about 1900 as saying that everything that there was to know about physics had now been discovered. All that was necessary was just to get the measurements of Is this to prove him right? Or
No, definitely wrong, because I believe, so he was asking about Lord Kelvin, who said that there was nothing to learn about physics, just to measure things. Actually, no. I don't think we had the standard model at all. I don't think we had all these particles, and I think the model we had of the world at that point was completely wrong. So I think I disagree quite strongly with him on that statement. Right, next question.
You talked about the accuracy you achieved with the Higgs. To put that in context, what accuracy have you achieved on the other particles like the top?
Yes, so that's an excellent question. So he was asking how accurately have we measured other particles like the top. Actually, if you look very carefully at the plot I showed you, well, you can't really see. Actually, the uncertainty is larger on the top quark. It's about a GeV. So it's at the percent level on the top. And the reason for that is how the top decays. It doesn't decay nicely to leptons and photons, which we can measure very accurately. It decays to things I haven't talked about at all, which are jets. So these are when you get quarks and gluons, and they make a whole bunch of particles, and you have to collect them up and try and figure out where it came from. And that actually limits how accurately we could measure the top mass. So that one we know very imprecisely. The one we know extremely precisely is the W mass. That was one I think I showed you on maybe day 2 or day 3. This is something that it decays to leptons, and also because it's a very important model parameter in the standard model, this one is being measured to greater accuracy. So it depends on the particle. Essentially, we try to measure them as accurately as we can, but we get limited by physics. You know, we can't measure everything. I think there was one, yes, over there.
In America, the Higgs boson is lighter than the top quark. How does the top quark then come from the Higgs boson? Where's the missing?
So it's an excellent question. So you're saying the Higgs is lighter than the top quark. How does the top quark how does it come from the Higgs? Turns out it doesn't. The Higgs cannot decay to top quarks because it's lighter. But there's another way the two can interact. And this I haven't shown you at all. There is actually another way to make Higgs bosons at the LHC, which is called top quark fusion, where you actually have two top quarks, they produce a Higgs boson, and then it decays. And so it's not in the decay that you see it, it's in how you make it. This is how they can interact, and that gives them the mass. That's actually something I work on as well.
Because your chart showed that most things were top quarks.
Yes, So it's from the production, which is not something I talked about. So it's indeed confusing. It's actually another way of making it. So in the end, right, what I'm actually talking about is the interaction. Okay? So what that means is if you put the two together, does anything happen? And I've mostly focused in this course on the decay. There's also the other side, which is in the production, which is, unfortunately, I didn't have time to talk about, but that's the other part of the picture. Any last question? We should probably keep going. Okay. So, who wanted to go beyond the standard model? One person? Oh, it's very disappointing. Only a handful? So we should stop? Okay, fine, I'm on holiday. We do. So actually here, by the way, the Higgs doesn't just tell us about the universe. It also brings up the question of, is the standard model everything that we have? Or is it actually part of something that's larger and more complete? And I'm going to tell you a technical term, but it's actually pretty easy to understand. This is something called an effective theory. Okay? Now, it sounds complicated. It's not. So everyone has a television, right? Or used to have a television, unless you have an objection to televisions. All right. And everybody knows how to make it work, right? You have a remote. Okay, or else your kids or your grandkids make the television work. But either way, there's a way to make it work and turn on. And the point is, right, is once you have the remote and you know how to switch it on and off, you can make it do what you want without knowing at all how it works, right? It doesn't matter. You just need to know if I push this button, TV goes on, push this button, it goes off. That's actually an effective theory. So you don't know all the details of what's going underneath. You have a theory, button on, button off. And that's the same idea, is that you can look on one level and you can see something and you can understand how it works, but there's actually something underneath. So this is the idea. Here's another example. Today, lots of equations. This is Newton's law, not a complicated one, right? Force equals mass times acceleration. That's actually an effective theory, because the real theory is special relativity, which doesn't matter much for day-to-day basis, right? If you have normal sort of things, car speeds, etc., Newton's laws work just fine. But if you go close to the speed of light, then it's actually not the whole thing. We need an extra piece, which is missing. And so that's another example of what can be an effective theory which works in some area, but doesn't actually work everywhere. And so we use them essentially all the time. This bit over here, so the question was what this is. Oh, so this is just a correction. If you take the full derivative, and it just says you need to actually change times by the velocity times the derivative of the mass with respect to time. The details doesn't matter. The idea of this is just to show you there's a piece missing, and that tells you the full story to do it. They're all okay. There's nothing wrong with any of these equations. All right, so the question was, the top equation's okay, why am I correcting it? The truth is the top equation is not fully okay. If one gets to very high velocities, very close to the speed of light, the top equation's actually not quite correct. And this is actually the difference, and this is why Newton's laws, they're not wrong. They're only valid in certain regions. They're part of a bigger theory, which is special relativity. And you can get them out. You can get back from one to the other. So back to particle physics. So remember all those forces we've been talking about, right? We've talked about the strong, the electromagnetic, the weak, and also gravity, which we half ignore. And there's one kind of interesting thing. Did you notice that I sometimes might have said electroweak? Have I said that a couple of times? Yeah, I probably said that. I didn't explain what I meant, did I? So it turns out, when you look at the forces as a function of energy, things change. So it's not the same picture at all energies. And actually, if you get somewhere around the mass of the Higgs, it turns out, the electromagnetic force and the weak force actually become the same. So that's why I call it electroweak, is they actually unify. And this is why I explained effective theory, because at low energies, it looks like they're separate. Actually, they're the same. We just can't see it when we're at those low energies. The same sort of idea. So that's really cool. This was something discovered in the 70s. It was really exciting. And this is what you do if you make a plot versus energy of all the different forces. And we actually make measurements. We can see like how the strength of the strong force actually varies with energy. And if you look at this picture here, what's the sort of obvious thing you might want to ask? Are they all going to go together, right? We have two which go together. Can we go to really high energy? Will they actually all go together? And so you can say, let's imagine that happens. and you can make a very pretty plot that looks like this. Now, anyone remember where the LHC will be on here? So this is a scale in energy.
125.
That's the Higgs boson. That's the mass. Let's think about the energy that we collide the protons at. It's actually 14 TeV. So this is 14,000 GeV, which is the axis. And here we notice we're at 10 to the 15. Way bigger. LHC is way down this end of the picture. And so if this happens at really, really high energies that we actually don't know how to make a collider to look at yet. Okay? So it's one of those things, this is an idea. Here's a different way around. Here, sometimes you can have ideas that are really, really hard to test because we don't know how to do it. Okay? So we don't know the answer to this one. And what you can see here is they have names. If you've maybe heard of a grand unified theory or a theory of everything, that's actually what they are. So grand unified theory is the idea that the strong and the electroweak become the same force. A theory of everything is, let's put gravity in there as well. Now remember I told you we don't know anything about the quantum theory of gravity? So it's pretty ambitious to try and get a theory of everything where we actually don't know anything about this line. So this one is really a long way around. Now, I wanted to point this out because of this. So the energy at which we might have the theory of everything is something you might have heard of, which is called the Planck scale. This is actually the highest energy we know that any of our physical theories could work. Beyond that, we have absolutely no idea. So we think it's sort of a maximum energy that one can have. And by the way, if you want to sort of ask, what is this 10 to the 19 GeV on sort of everyday terms, I can convert it into mass using my favorite formulas. It's about the mass of a flea egg. Flea egg, random choice. Something very... Yep, the theory. But of course, that's entirely cheating, right? Because a flea egg is way bigger. When we're thinking about this, we're thinking about it, on a really microscopic scale. And so it's weird. This is a bit of the sort of tension between the things we're doing on very small particles and everyday life. It's hard to compare.
What would extra energy do? Get you closer to the speed of light? What's the purpose of it?
Yeah, so the question was, what would happen if we went past the Planck scale? We actually don't know. So every single equation that we have is invalid if we go past there. So it's same question you might ask, like what happened before the universe was created? We don't have an answer at the moment. And we can't get there. We'd love to get there. That would be very exciting. But we don't know how to. Yeah. So we don't actually know. So the question was, where in the universe does the theory of everything exist? Actually, we don't know if this is true. This is an idea. Okay? And we really don't know if this one is true or not. It might be, it might not. And the answer is, even if it is true, it doesn't exist anywhere right now. It could have existed very shortly after the Big Bang. So if it does exist, it could have existed after the Big Bang, but we really don't know. This is speculative.
3 light years across.
So we would love a Hadron Collider 3 light years across. That'd be awesome. In fact, actually, I'm trying to build a 100-kilometer one, which is a bit more modest. But the truth is, like think about the speed of light, right? You can accelerate particles very, very close to the speed of light, but you can't actually quite get there. So we don't even know even if I had infinite money and infinite space, it would even be possible to get up there. I would take a bet that as you got close to some sort of final scale, something weird would start happening. So one would love to get there, but yeah, we don't know. If you gave me infinite money, I can't go test this. I actually don't know how to do it. Yes? It's not capable to, so the question was, as I said, I don't know how to do it. Is it not capable to extrapolate with mathematics? No, the problem is like if you take the mathematics and go there, you get things that just make absolute nonsense. So unfortunately with these theories, it's quite easy to make nonsense. And all that tells you is you have the wrong theory, right? So if there was a theory there, it's a different one from the one that we know, and we don't know what it would be just yet. So speaking of nonsense, I'm going to tell you about a problem in the standard model. Okay, so these are the Feynman diagrams. Remember, I've shown you a few times. And what we want to think about is, let's imagine we have a Higgs just standing around, okay? Now, the Higgs can interact with everything, and here comes your top quarks, you were asking. And it turns out you can actually pop out a pair of top quarks temporarily, and then make them disappear, and then have your Higgs boson again. Okay? This is something that can happen. Actually, you can do it with all the particles, but it's the top quark that's really the one that causes some of the problems. And the problem is if you draw this picture, and then you write down the equations that it actually means, and you calculate what is the Higgs mass, the answer that you get is infinity. Oops. That's a problem. Because we're pretty sure it's 125 GeV. I showed you. We know that. It's absolutely not infinity. And the problem is this loop, it's divergent. Anyone remember doing integrals? And sometimes your integral just doesn't work. It diverges. Same thing, but in the thing. And the reason for that is because when you do the integral, you actually have to do it all the way up to this Planck scale that I was talking about. And this is actually where the infinity comes from. So if the Planck scale was at the same as where we are today, wouldn't be a problem. And so this problem is, the Higgs mass is not infinite. That's clearly wrong. And so one way you can formulate this is you can say, why is the scale at which the weak force happens, which is, the mass of the Higgs, around 100 GeV, and why is the Planck scale, why are those so different, right? And this is how you end up getting this 10 to the 24 ratio between the two of them. Or you could ask it another way. If the Higgs boson had a mass of the Planck scale, everything would also be fine. So why is it lighter? And this has got a fancy name. It's a very important one. It's called the hierarchy problem. The reason it's called hierarchy is because we're talking about different scales. Okay, so you see I was talking about differences between what happens in the Higgs or what happens in Electroweak and what happens at the Planck scale. And hierarchy is just saying these are really far apart and we just don't know why. So this is a pretty big problem, right? We found a Higgs and immediately we've just said the standard model doesn't work, haven't we? That's not good. This one we don't know the answer to, by the way. Which thing? This. Oh, sorry, it's an anti-top quark. I did not explain it. So I said it's a top and an anti-top because we need to conserve charge, actually. And normally we indicate antiparticles with a bar to do it. I should have explained that. So there's one answer to it. Someone might have heard of supersymmetry. Anyone? Yes. So supersymmetry is a very nice theory which says, actually, there are a whole bunch more particles than all the ones I told you about. In fact, there's a copy of every single particle that we have. And the reason that's useful is it means that we have this diagram, and then we would have this diagram. Sorry, the circle should be in the same place. I just drew it a bit funny. It means the same thing. And this guy with a little wiggly tilde on top, that's called the squark. It's the stop. Okay? So it's the supersymmetric partner of the top quark. And the reason that this works is because you get one set of equations for the top quark, one set of equations for the stop, and they cancel. So instead of having infinity, you cancel out the two sets of equations and you can get the Higgs mass of 125 GeV. That's pretty neat, right? I just told you everything was broken. This is it. Unfortunately, this is one of the things everyone was really excited for to look at the LHC. So far we haven't found supersymmetry. We've looked in all sorts of ways. It's not fully excluded yet because there are a whole bunch of different ways you can do it, but so far we don't find it. So this might be a different sort of example of where there's a really nice theory that might not be true. These things can happen. We don't know yet. Maybe I'll be back in 5 years saying, here's supersymmetry, now we measured all the particles. I'd be happy to be wrong in that way. So yeah, Higgs mass, kind of important. We know the mass, but we actually don't know why it has the value that it does. And all the ideas that we've had so far actually haven't worked out. So that's good. I'm a scientist. This is a good thing. We want to not know things. And we want to really have questions that we actually don't know the answer to. So I have just 5 more minutes. I'm going to just tell you one more thing. Anyone know that picture? Yes. So we've talked about it a few times, but I think it's good to mention it now, that the LHC in some sense can be thought about as a time machine. Okay, and I don't merely mean a time machine. That would be useful. I could do a whole bunch more work if I could go back in time. What I actually mean is that we're going back in time and looking at the early universe. Okay? Anyone seen this picture before? There's lots of these ones. So the idea of it is, here's when the Big Bang would have happened. Okay, and this axis is time. And we're sitting, today over here. Okay? This picture is online. It's on this PDG site that I said, so you don't need to take a picture. And I don't think you can read them, but actually what's written on the axes here is what time we were talking about and what energy that we actually had in the universe. Okay? And we're here today. Just to tell you, I can see the numbers. We're at 10 to the 9 years. Okay? This is where we're sitting over here. Where the LHC is, which is actually over there, is actually at 10 to the minus 19 seconds. Okay? So this is a very compressed plot. Okay? All the stuff that's happening here, this is all happening in seconds, and then suddenly we jump, into many, many years. So don't think about this as a linear sort of thing, right? It's very non-linear. It's because all the interesting stuff happened really, really quickly in the beginning of the universe. Yes?
I hear you correctly that the energy therefore increased.
Now? Today?
From there to here.
No, decreased.
Decreased. But I thought there was a complete conservation of energy.
Exactly. This is exact. So the question was, did the energy increase or decrease? Actually, the answer is exactly what you said. It stayed the same. The reason is it's the energy density that has decreased because the universe is expanding. Right? And so it's expanded hugely, and the energy is conserved, but the energy at each point has indeed gone down a lot. Okay, so someone wanted to know the temperature. Who was asking about the temperature? There we go. So I looked it up for you. For the LHC, where we're at an energy of 100 GeV, it's 10 to the 15 Kelvin. Okay? It's pretty warm, right? We might need some aircon if we were at 10 to the 15. No, actually, we'd be dead, right? Very, very long dead, actually, if we were at this temperature. And it's actually very easy to convert between temperature and energy. There's an equation which is using the Boltzmann constant. So you're actually just dividing to get between the two. That's why I use them fairly interchangeably. By the way, notice the energy is 100 GeV. This is actually around about the mass of the Higgs. That's not a coincidence, because that's actually the Electroweak scale. Okay? This is actually around about, doesn't matter in this sort of plot if we're within a few things. And so the point is when we have the LHC, we're actually going that far back in time, and we're actually probing this part of the universe. And that's pretty exciting, because there are not so many ways we can go and have a look back there, right? In fact, there are two ways, not just one. And the two ways are colliders, which is what we've been talking about here, and also these gravitational waves that you might have been hearing about. These are actually also a way where we can start actually learning about what happens in the early universe. So I think I'm going to stop here. There are a few more slides online. You can have a look at them, and let's see if there are any last questions.
Sorry, you've given us the temperature of 10 to the 15 K.
Mm-hmm.
But put that in a context, like the temperature of the center of the sun or anything.
Nope.
No.
So the question was, can I put that temperature in context? And the answer is no, because it's far hotter than absolutely anything in the universe, by far.
Thank you.
So,
That's an answer.
yeah, no, that's an answer. So the thing is, the conditions that actually happened after the Big Bang, these are far more extreme than any conditions we have here. And that's actually the reason why we can't study them. So if it was that hot in the center of the sun, then I could have studied the Higgs boson by studying the sun. But this is just far, far hotter to do it. So just think about it as being really painfully hot. Yes?
What does that mean that there are no Higgs particles out there anyway?
So the question was, does it mean there are no Higgs particles out there? Can I say yes and no?